In this lesson, we're going to continue our examination of counting techniques. So we're going to look at permutations again, the idea of we've got objects, we won't put them into groups. But we're going to look at what happens if we have some identical items. I'm going to start with an example here. So I want to look at the different permutations for these words. The word's dole. Now the word dole has 4 distinct letters. So when I decide permutations for it, I've got 1, 2, 3, 4 spots to fill. And I got 4 choices for the first letter, the D, the O, the L, the E. And then 3, and then 2, and then 1. So I have 24 different choices, right? 4 factorial. Okay? But the challenge happens when I look at the next word, the word doll. So if I look at the word doll, and I look at the permutations of that. Now, permutations means what are the different orders we can put it in. So let's make a list of them. I start moving some letters around. Okay? Now, these aren't words. These are just permutations of the letters. Right? We consider these words just as in they have distinct letters in them that you can tell apart. Okay? So there's 2, 4, 6 of them. I've moved some of the letters around, the O's and the L's and D's. But there's some more I can do. Hopefully I don't repeat any here. I don't think I will. O, L, D, L, D, L, O, L, L, O, D, and L, L, D, O. I think those should all be different. All the ones that are D, and then O, then L. So it turns out that I don't have as many anymore. I've got 1, 2, 3, 4, 5, 6, 12. I've got 12. Which seems like, hey, I got half of that, right? It's just divided by 2. Okay. Well, if we take one more example, let's look at the word lol, L-O-L-L, and look at its permutations. So I have L-O-L-L, or L-L-O-L, or L-L-L-O, or O-L-L-L. I got 4. Okay. Which seems like, well, there's a combination again here. I can divide by 3. Right? 12 divided by 3 is 4. But how do I know from the very beginning that I have 4 different combinations of these things without having to go through them all? What idea can I use? Well, if we stop and think for a second, this first question had 4 factorial things, 4 different things. I could tell them apart. And when I divide that by 2, I got my answer for the blue ones here. But really, there was 2 things that were the same. So let's think of this as being 4 factorial divided by 2 factorial. Okay. And when I had 3 things the same, it turns out I could just divide my previous answer by 3 again, or in other words, I could divide it by 3 factorial. That's what that 3 comes from, right? 3, and then 2, and then 1. There's this. Okay, so there's a little formula for us we can remember or write down. If we have things that are identical, we can't tell them apart. They're the same. The total number of permutations is always given by n factorial, the number of things you have altogether, divided by, and you can put brackets around this, okay? A factorial times B factorial times C factorial, where A, B, and C, and so on are repeated things that we can't tell apart. In the previous question, there was 4 letters, and in lol, there was 3 L's I couldn't tell apart. So let's look at some examples here. We have 7 sheets of colored paper on Shannon's desk. There are 4 sheets of blue and 1 each of red, yellow, and green. How many different ways can she stack the paper? Well, so this is orders. I can tell apart. I got a blue, then a green, then a blue, then a green. I can tell that apart from blue, blue, green, green. So I'm using factorials. There are 7 things altogether, and there's 4 blue ones. They're repeated. They're identical. Now, theoretically, you could also put in the 1 red, and the 1 yellow, and the 1 green. But that doesn't really make sense to put in there because 1 times 1 times 1 is still just 1. So we don't usually show that part. And our answer comes up to 210. Take a look at the next one. In how many ways can the letters of the word Mississauga be arranged? So Mississauga is made up of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 different letters. But some of those letters I can't tell apart. They're identical. For instance, I have 2 I's, 4 S's, and 2 A's. I can't tell them apart. So because I can't tell them apart, I can't say, hey, I moved them. when I can't see that, I can't tell that. So I have to divide them out. Now be careful here. We're going to use brackets. Okay, we want to figure out what that bottom number happens to be. If you do this properly, you should end up with 415,800. I'll try a couple more little examples here. We got Yuri. He's shelving books into display in the school library. He has 4 different books with 3 copies of each. In how many ways can you arrange the books on the shelves? So altogether, he has a bunch of books. How many? Well, 4, 3 copies each. He's got 12 books. But some of them he can't tell apart. He can't tell apart the 3 copies of the first book. So there's 3 of them. And 3 copies of the second book, and 3 of the third, and 3 of the fourth. They can't be told apart. So I have to divide them out. I can't say I move them when I can't tell that, right? So we end up with 369,600. Okay, let's do a slightly more tricky one here. Find the number of ways of rearranging all the letters of the word Tennessee if there are no restrictions. Okay, no restrictions means any way possible. So let's count how many letters we have. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's divide out anything that we see that's identical, we can't tell apart. So we've got 1, 2, 3, 4 E's, and we've got 2 N's, and we've got 2 S's. I can't tell them apart, I have to divide them out. And if we do that, we should end up with 3,780. Okay, let's try the tricky one now. If the first 2 letters must be E and E, so what are we really rearranging? Well, if I put an E and an E in there, use up an E and use up an E, let's pretend it's these 2, it's like they don't exist anymore. They've been used up, they're gone, and so are their spots. So I'm left with the remaining letters, 1, 2, 3, 4, 5, 6, 7 of them. And of those remaining letters, we have 2 E's, because remember the 2 E's at the end are gone, right? That we've used them up, they don't exist anymore. 2 N's and 2 S's. So like we did with regular factorials, once we've put something in place, it's gone, used up, we don't have to worry about them anymore. 630. What if the first 2 letters must not be EE? Well, that's one of our counting techniques, right? If we take our total and subtract start EE, what are we left with? We're left with ones that are not starting EE, the complement, if you will. So our total is 3,780. The ones that start with E and E are 630. And we're left with 3,150 ways that are not EE. Okay, we'll try some other trickier ones. Things we've seen before, but with a little twist on them. So we got 6-digit numbers. How many can be formed if you have the numbers 1, 2, 2, 3, 5, and 6? In other words, there are 2 2's. What if there's no restrictions? Well, we've got 6 things, and we've got 2 2's, can't tell them apart. We've got 360 different ways. What if they must be less than 300,000? Well, making them less than 300,000, they're telling us a starting value. They must start with either a 1 or a 2. If it starts with a 1, I fill that spot in, I'm only left with 5 things to arrange, and 2 of them are 2's. However, if I start with a 2, I still have 5 things, but no repetition anymore, because one of the 2's has been filled in. It's in the starting spot, which means this answer is 120. And we know we have this mutually exclusive idea. Either start with a 1 or start with a 2. That means I have to add them together. So I get 180 different numbers that are less than 300,000. What about more than 300,000? Well, there's 2 ways we can go about this one. I could start the same way and say, what could I start with? A 3 or a 5 or a 6? Or I can think about my complement. My total minus less than 300,000 will be left with ones that are more than 300,000. It's not possible to get exactly 300,000 in this question, so these 2 things are complements to each other. In other words, 360 minus my 180 means there are 180 ways of getting more than 300,000. Let's try D. It must be even. Well, things that are even have to end with even numbers. So what could I end with? I could end with a 2, or I could end with a 6. Okay? I don't have the number 4 in here, notice. So what happens if I end with a 2? It means there's 5 additional numbers and no repetition. The 2 has been used up. But with the 6, there's 5 additional numbers and 2 of them are 2's. So this looks pretty much like the odd number ones. So I've got 108, sorry, less than 300,000 ones. Okay, last one. The number must be even and less than 300,000. So now I've got two conditions, even and less than 300,000. So I got to think about my start and my end. It's going to be less than 300,000, so it could start with a 1, and be even, so it could end with a 2. Or start with a 1 and end with a 6. Or it could start with a 2, because that's less than 300,000, end with a 2. Or start with a 2 and end with a 6. Those are all the different cases. But in all these cases, we have 4 numbers left in the middle. So in the first one, 4 factorial, I have no repetition of 2's because one of my 2's is already used up right here. The next one, I have 4 factorial again. There's 4 numbers, but 2 of them are 2's. Somewhere in this connection here, there's got to be 2 2's. The third one, just 4 factorial, the 2's been used up. And the last one, 4 factorial, the 2's been used up. Just out the front this time. So we end up with 24, 12, 24, 24, and the word or between all those things. So we're going to have to add them all together, and we end up with 60 different combinations of things that are less than 300,000 and even using those digits alone. Okay, last idea. Okay. How many arrangements are there of the letters A, B, C where the consonants stay in the same order? And we're going to do this with an example again. We're going to look at them. We're going to write them out. So I want the consonants to stay in the same order. So A, B, C, that's the same. Okay, that's our first one. Or B, A, C, the consonants are still in the same order. They're separated, but they're still in the same order. Or B, C, A. There's no other combination where we have the B followed by the C. Okay, so in other words, B and C are basically the same letter, and the A is being arranged around it. It's kind of the same as thinking of it like this: ABB, BAB, or BBA. They're the exact same number of combinations. So in other words, we can think of the letters where they're staying in the same order as repetition, identical items. There are 3 things all together. I want the B and the C to stay in the same order, so 2 factorial. I can't move the B and the C around. Treat them the same. With that idea in mind, let's try this last one. And this is just your formula here, okay? If n distinct objects need to remain in a specific order, divide by n factorial. So in the previous one, we had 2 things to stay in a specific order. We divide by 2 factorial. So we got the word number. Oops, sorry, moves that back there. The word number. How many different ways are there to arrange the letters in the word number if the consonants must remain together? And then part B, in the original order. So 2 different questions here. Letters together or letters in the same order? Well, if I want the consonants to be in together, I've got 1, 2, 3, 4 of them. I don't care what order they go in. There's 4 factorial ways of doing that. And don't forget, we still got to rearrange those vowels also. We got 2 of them. Okay, so my order is I got my N, my M, my B, my R, my 4 things, and I got my U and my E. So I've got really 3 different things to arrange there: my group and my individual items. And within the group, there's 4 factorial ways of doing that. So we're going to have 144. But if I do the second one in the original order, the N, the M, the B, and the R, they can't change the order. I can't do the 4 factorial at the beginning. That doesn't matter. I can't change them. So what I need to really think of this as is, well, it's basically like having 4 letter N's, a U, and an E. So I've got 6 things altogether, and I've got 4 of them that happen to be the same. there's only 30 ways of doing things where they're in the original order. And so that's kind of a tricky idea. Do I want them together, or do I want them in a specific order? And depending on the way it's worded, you have to approach them in two different ways. And I got some questions for you to try again, as usual. Some things you need to practice on. Give them a try. They're all different. It takes a little bit of practice. The more you do these, the better and easier it'll get.